It says that the work done to move a charge of some magnitude is given. If the charge was started from rest and ended up with a certain amount of kinetic energy, what's the potential energy difference from A to B? Okay. We know that the work is equal to 15 times 10 to minus 4 joules. We know that the charge is equal to minus 8.5 microcoulombs, which equals minus 8.5 times 10 to the minus 6 coulombs. We also know that it ends up with, so Ke final is equal to 4.82 times 10 to the minus 4 joules. Let's try to simplify this and think about what's happening here. First of all, if A and B were at the same potential, so the same voltage, then all of the work would go into kinetic energy for the final thing. This is what I like to call a butter analysis. Okay. If you had 15.4 joules and your potential energy didn't change, so this is all the work that you put in, then your kinetic energy at the end would be equal to the work that you started with. This is for VA equal to VB. Alright, but we actually have less kinetic energy. So a lot of that had to go to raising the potential energy. Now remember, when you have a negative charge, so I've got a negative 8.5, they're kind of oddballs because the higher the voltage you go to, the lower their potential energy, because that means you're getting closer to positive charges and they're happier. So what we know is that because we're missing some of this work, it's not going as fast as we would expect, there has to have been some increase in potential energy. And to do that for a negative charge, you have to push it closer and closer to a negative charge, a lower voltage. So this must be the potential at A. This must be the potential at B. So if you imagine what would cause this, there might be a lot of negative charges over here and a lot of positive charges over here at at A. And so the electrons want to stay at A. You have to actually do work to get them to go to B because they hate being next to these other negative charges. All right, so now let's have a look at our butter analysis. Now we've got, let's do, potential energy we'll say is about this much. And we've got a little bit of kinetic energy over here that takes up the rest. So we've accounted for all of our butter. The work that we put in has to change potential and kinetic energy. Since we're given kinetic, we can find potential. So work equals the potential energy plus the kinetic energy. Fair enough? So you take this much butter and you add it to the red butter and you get all of the work that you had initially. Potential energy then is equal to the work minus the kinetic energy that we had at the end. So this is all of the energy that was put into the system that didn't turn into movement, basically. But we're not looking for potential energy, we're actually looking for the potential difference. This is delta V, which equals V final, VB minus V initial, which is VA. So now the potential energy we know is equal to Q times that potential difference. That's the electrostatic potential energy. We already know that that was written as work minus the kinetic energy. And we can now solve for what we actually want, which is the potential difference here. Alright, so the potential difference is equal to work minus the kinetic energy that was given, all divided by the charge. Now we just need to plug in some numbers. So delta V is equal to, well look, these have the same order of magnitude, 10 to minus 4 joules. So we can just take 15 minus 4.8, that's about 10 times 10 to minus 4 joules on top. And we divide by the charge, which is minus 8.5 times 10 to the minus 6 coulombs. A joule per coulomb is a volt. This is a little bit bigger than 1. It's more than 10%, a little bit less than 20% more than 1. So I'm just going to say 1.2. And now I need to take care of this. This is 10 to the minus 4 divided by 10 to minus 6. That is 10 to the minus 4 plus 6 minus minus 6, so plus 6. And that equals 10 to the 2. Alright, times 10 to the 2. So that's telling me 120 volts. And there's a minus sign that I forgot. That just tells you that B is at a lower potential. So if you called this 0, you can call 0 volts wherever you want, basically. Then this would be, A would be at 120 volts of potential.